AP Physics for Unit 4, Work, Power, and Energy. We've already talked about systems and how systems can work in terms of taking energy into or taking energy out of, the difference between an open and a closed system. So now we're going to go into a little bit of detail on the equation for work and what work actually is. So if you're taking an object and you're moving that object, in order for it to move, you're going to have to give it energy. So the definition for work in and of itself is that transfer of energy, okay, that transfer of energy to or from a system by any external forces, and these are forces that are outside of the system itself. So in other words, you have to give something energy to make it move, or you have to give something energy conversely to make it slow down. And there are two interpretations of this formula. One of them includes an angle, and the other one does not include an angle. So the first one just tells you that work is going to be equal to the force, the outside external force that's applied, times the displacement that occurs. And the other formula interpretation is going to tell you that work is going to be equal to the external force times the displacement times the cosine of the angle between the two vectors that happen. So if we look at case number one would be like taking an object and you're putting an external force on it. So let's say that somebody's pushing on this side of the box over here. So you'll have a force acting on it. And the displacement that it travels would be the displacement horizontally as it goes from one location to another. So the displacement vector would be from this position to this position. Notice that it's got like a parallel line here. This means that your force and your displacement vector are in line with each other. And what's going to happen after that's done is the object is going to end up right on the other side, and it had to take energy to move it from one spot to the other spot. So in order to find out the amount of energy that it took, that transfer of energy, that's going to be this external force times this distance, or I'm sorry, this displacement. I shouldn't really say distance here. I should say this external force times this displacement is going to be the amount of energy that was required. Now, normally, whenever we measure out our forces are measured in newtons. And whenever we measure out our displacement is going to be measured in meters, which means that if we take these two quantities and multiply them together, you're going to get newtons times meters, which we normally call joules, which is a capital J. That's Joules, joules, which is a capital J. In order to think about like what a joule is, it's a really, really small unit for energy. It's about the amount of energy required to take an apple and just slide it across your desk. It's not really a huge amount of energy to be able to do. So whenever we see problems like this, getting answers in the thousands of joules or even tens of thousands of joules is completely reasonable. So let's look at this other case over here. You've got FD times cosine theta, which is the external force times the displacement times the cosine of the angle in between them. Well, this would be like as if you're taking a box, but instead of pushing at a straight line with the displacement, you would be pushing either upwards or downwards. So I'm just going to take the force and kind of put it diagonal like this and say that, well, our force is going this direction. In this case, that you're pushing the box upwards, so you're not pushing it straight in line. So that's going to affect the amount of energy that you put into the system. So I'm going to put my displacement here. It still moves a distance as it goes from one spot to the other, but now there's an angle in between these two. So for this angle between, we'll say that this angle is the letter theta. That's going to be your force, external force applied to the object, times the displacement, times the angle between the two vectors. And whenever you see this cosine of theta, you're always going to interpret this cosine of theta as the difference between the two vectors. Okay, your force will still be in newtons, your displacement will still be in meters, you'll still get joules for your answer, but what you're really looking for here is you're looking for the cosine theta will give you the horizontal component that is in line with the displacement vector. So that's ultimately what we're looking for. Let's look at a couple of case examples for how this would actually work out. So here's a whole lot of different scenarios that we have over on the right side. I'm going to see if I can try to squeeze most of them in. Looks like I can get 4 of them. If you look at the first one, it looks like the angle is equal to 0, and that means that the displacement that gets traveled, this will end up giving you the maximum amount of work applied to the system. This will give you the maximum energy transfer, which means that if we had a velocity at the very beginning, so let's just say that, the velocity vector up here is going to be 1 bar, and I'm going to put VI for that one. By the end of it, this would be a larger velocity for the final velocity. And let's just go ahead and give it 3 bars to indicate that it went a very large amount. I don't know. So your initial velocity is going to be slower. Your final velocity will end up being faster. So this energy transfer transferred energy into the system because your force vector is going to be right in line with your displacement vector. Okay, if we look at the next scenario down, that's going to give you an angle that is less than 90 degrees, but not straight up 90 degrees. So this will give you the same scenario, because remember, it's the force times the displacement times the cosine of the angle in between them. So if we started off with an initial velocity of 1 bar, then the final velocity over here wouldn't be as large. So let's go ahead and kick it down to, like, I don't know, maybe like a bar and a half or so. Okay, so the the energy transfer won't be as much. You're still putting energy into the system, but you're not getting as much energy into the system because you're just not pushing straight in line with the object. So this FD cosine theta, the cosine theta is going to end up being a smaller component, so you're not going to get as much energy as if you were straight pushing it right in line or parallel. Okay, and if we look at the next one, well, okay, this one's right at 90 degrees. And in this case, there's not really going to be any work being done. And the reason is because the cosine of 90 degrees ends up being 0. And, realistically, whenever you look at it, you're not putting any force horizontally inside this displacement. Because if it's force times displacement that are in line with each other, this is the opposite of being in line. So over here, the work being done in this case is equal to 0. You're not actually doing any work whatsoever. And whatever the velocity was at the very beginning is going to be the velocity at the very end. I really didn't give myself a lot of space here, but let's say that you had 1 bar of VI at the beginning. Your final velocity is going to be exactly the same. In other words, you didn't put any energy into the system. You can put a force on things and not actually put energy into the system. In order to put energy into the system, it has to either move, it has to go some kind of displacement, or there has to be some kind of acceleration or force acting on the system. If there is no displacement that is covered, no work is being done, regardless of if you have a force applied to it. There has to be motion. There has to be some kind of motion from one spot to the other in order for there to have work be done. So now's probably a good time to bring up some ideas on the cosine, because if you think about the cosine itself, some of you have had trig and some of you haven't had trig. But this is basically what it's going to end up looking like. When you're right in line with each other at 0 degrees, which I probably need to write 0 degrees right there. So if you're at 0 degrees, you're right in line with each other, and the cosine of 0 is a maximum value of 1. As you continue to go from 0 to 90 degrees, the cosine decreases over time. So the cosine of 30 gives you a smaller value. The cosine of 45 degrees gives you an even smaller value. The cosine of 60 gives you 1/2. And if you don't remember these numbers, they're on the AP Physics formula sheet, and you can use those. What's not on the formula sheet, and important to remember though, is after you go past 90 degrees, you start getting the same numbers that you had on the other side, but they're just flipped over, they're negative. So as you continue to go from 90 degrees to 180 degrees, you have the exact same shape of the curve, just flipped over or reflected. And it ends up bottoming out at -1. So the cosine of 80, or sorry, the cosine of 180 degrees ends up being -1, which is like the lowest or the most negative value that you can get for the cosine. Okay, so if you're moving from 90 degrees to 180 degrees, it flips over into negative values. What this means is we can determine whether or not we're doing positive work or negative work, because when you do a work problem, you're going to end up with some negative answers sometimes. Negative answers for work usually means that an energy transfer is occurring outside of the system as long as you've set up your positives and negatives correctly. And another little reminder here, so like if you have a force applied to an object, you can break it up into its components. The horizontal component will be based off of the cosine, and the vertical component will be based off of the sine, as long as you have your reference angle based from the horizontal, which for work problems, I highly recommend you do that. All right, so let's look back over here at the last two situations. In the next to last situation, the displacement still occurs, but the force being applied is now greater than 90 degrees, but not straight up 180 degrees. And what happens whenever you do this is you're going to start doing what's called negative work. Okay, so you're going to start actually transferring energy out of the system. So if this thing, since the force, since the horizontal component would be going this direction, if you're basing it off of the horizontal, then if you had a velocity set up, and let's say that the velocity was, 3 bars to start with, I'll put VI for initial velocity, then that means that on the other side, the final velocity is going to end up being a slow down. So the final velocity will end up being slower. Okay. And then likewise, if the angle is right at 180 degrees, this gives you the complete opposite of them being in line with each other. They're in line with each other, but they're in the completely opposite direction. So once again, what's going to happen is you're going to get negative work to happen on this. So if you started off with a velocity that was much larger, this is going to decrease the velocity by a even greater amount. So we'll say that that velocity decreases even more compared to the situation above. And the difference is this one is applied at an angle and this one is straight back. Okay, so this is going to be the maximum. So this is going to be the max transfer of energy out of the system. That's going to be the maximum transfer out of the system. Whereas the one up top, where they were in line with each other, this is going to be the max transfer of energy in to the system. So if they're in line with each other, this will give you the greatest change in velocity. If they are opposite from each other, this is going to give you the greatest decrease in velocity, or the greatest change in velocity in the opposite direction from what you were intending. So if you're doing positive work, this usually indicates either a speed up. If you're doing negative work, this usually indicates a slow down or a negative acceleration, at least until you're going. If it was positive, you would be slowing down. Okay, so keep in mind though that once you start going backwards, the situation starts to change, because then you would be accelerating again. So be careful with your signs and what you do with it. Okay, so these are the situations that could happen from work, and this is a big breakdown of the situation of how FD cosine theta would actually work out in a scenario, in pretty much all scenarios. So I hope this was helpful to you guys, and I will talk at you later.